All right, gang. Mass 6610. Post-hoc comparisons are when we run our ANOVA and it turns out that the results are significant, p-value is less than 0.05. We want to dig deeper and see what pairwise comparisons are significant. In other words, why did we reject the null? Because again, circling back, the null hypothesis is that the group means are equal, and that the alternative hypothesis is at least one pair is statistically significant and different. So that's the purpose of the post-hoc comparison. So just thinking a little bit about type 1 error rate, I think I mentioned this earlier, that the reason we don't just compare means in the beginning, do a bunch of multiple comparisons, is because the type 1 error rate would be inflated. We can approximate that by taking 1 minus 0.95 raised to the k power. I think in fact, I know I demonstrated that in a previous video. Well, we know from other videos the type 1 error rate is related to power, because as our type 1 error rate goes up, our type 2 error rate goes down, vice versa. And then our power is inversely related to type 2 error rate. So if we control the type 1 error rate, we're going to inflate the type 2 error rate, which is going to deflate or lower the power. So we get a trade-off, don't we? And we think of that, and at least we identify a conservative test where we control the probability of a type 1 error. But the trade-off again is we have a high probability of a type 2, which leads, of course, to a low power. Now, there are many post-hoc comparisons. I can think of Holm, I can think of Tukey and Bonferroni, and all of these do a pretty good job of controlling the type 1 error rate. The problem is they sometimes do not have adequate statistical power. Now, what does that mean in lay terms? What does it mean not to have adequate statistical power? It means if there is truly a difference, we may not detect it with our test. So, drum roll, please. Which one is best? Well, it just depends, really. Uh, if the number of comparisons is small, a lot of people will say use Bonferroni. What's small? I typically think of 5 or less. If the number of comparisons is large, a lot of people will say use Tukey. A third option is the Holm test. As I mentioned earlier, again, it's just kind of all confusing because the research is confusing. When you have all these different combinations of probably a balanced design versus an unbalanced design, equal variances and not equal variances. Do we have no and what if two of these are met and one isn't? So there's all kinds of different combinations there that lead you in a direction to use a test which is better than the other ones. So I'm not going to go through all that because I can't possibly cover all the possibilities. So your choice will really depend on your situation. When you get to your master's thesis component, the research, you'll just have to analyze what you have, and then I would just Google it. The best multiple comparison for ANOVA given unbalanced design and unequal variances, and see what you get. So, the main thing I think I can share with you at this point is I can't cover all the possible situations. So this is just going to be an introduction to a couple of the basic ones. So I think at the end of the day, if we have equal sample sizes and equal variances, I would tend to go with Tukey. Tukey is the one that I always use. I always report, just because I think he's one of the greatest statisticians ever. So I depend on him, right? But a lot of people will say that Bonferroni is the most conservative test and that it does the best job of controlling for a type 1 error rate if that is your concern. So how's this all work out? Works out pretty cool, actually. So again, first of all, let's run our model. And take a look at the results. And again, tunnel vision, and we've seen this before, so there's no drum roll, please, aspect to this. We have statistical significance, so that tells me that we've rejected the null. So at least one pair of means is statistically significant. All right, so let's run the Tukey first. The Tukey command is just Tukey HSD. The HSD stands for highly significant difference. So it has a little bit more power and it allows us to, I think this is the way to set the confidence level. I believe the 0.95 is the default, but I want you to be aware of that in case you want to calculate a different confidence level. Now, I really, really like the way that the Tukey HSD output looks because it gives us the mean difference and then it gives us the 95% confidence interval for this particular comparison, comparing Professor B to Professor A. And then it gives us the adjusted p-value. So if we look down through here, we can see that the confidence intervals that don't contain zero are going to be statistically significant. The confidence intervals that contain zero are not going to be statistically significant. So the reason that we rejected the null, the reason that we have this p-value less than 0.05 is because Professor B students do about 9 points lower than, well, for the sample, they performed 9 points lower. And Professor C's students scored 11 points higher than Professor B's. Again, C and A, Professor C and Professor A, there doesn't, the difference in the quiz scores for those two is not statistically significant. Now, if we want to run the Bonferroni, what I would do is just use what's called a pairwise T-test. And we're going to use the outcome variable, which would be the values. And then the independent variable, the grouping variable is the independent. We want to, it has an option of doing paired. We want that to be false. And if we were doing a dependent samples nature test, then we would have a paired equal true, but that's not what we have here. And then we're going to do what's called the p-adjust method. And I'm going to do the Bonferroni. Now, the Bonferroni, the only thing that this output gives us is the p-value, so it are the p-values. And you can see that the p-values are a little bit higher, as we would expect. The Tukey test is a little bit more powerful. The Bonferroni test is more conservative. And you can see that the 0.002, or I'm sorry, 0.0022 versus 0.0021. So not a lot of difference. But, you know, there is that line in the sand of 0.05. I mean, you could probably visualize it. In one case, you could get a p-value of maybe 0.049 and a p-value of 0.051, where one is significant and one is not significant. Another option, let's just go back up and get that same command. And let's change this to home. And you'll see that the home is, what's going on here, BC. The home comparison uses a pooled standard deviation, just as this one does. Interesting. I wasn't expecting this, I have to tell you. The home is more aggressive. So I'm assuming that it does a um, less adequate job of controlling for the type 1 error rate, because for these two cells right here, it has generated a p-value that is quite a bit more aggressive, right? There's actually another one, if I can, if I can remember it. I know there's the Benjamin Hochberg, um, and I believe I'm going to regret doing this. Okay, no, I did get it right. And it's even a little bit more aggressive. Um, you can tell that this one's remaining stable across all three, and this remains stable in comparison with the home and uh, the recent test. And then, but this has a lower p-value, so it's actually more aggressive. So interesting stuff. And I would encourage you to just compare these tests to a pairwise t-test with these values. I'm not going to do that in this video, but it's pretty interesting to see how you control the type 1 error rate, and how it affects the p-value. The reason I don't want to get into that, because I'm afraid I'm going to get into a rabbit hole there and end up creating a video here that's much longer than what I want. So let's move on to the effect sizes for multiple comparisons. So what I want to do here is I want to calculate the effect size for the Tukey. Well, it's for the, let's go with the C to B comparison. So if I come up to the B to C comparison, I can see that the difference is 11.1111. So that is going to go right here. Right? So the difference in the means, and of course it's absolute value if we chose the -9 to be 9. And then the mean square within is going to be 37.24. All right, so we can put this in R. And the effect size is 1.82. So the legend that we use for Hodges G is 0.2, 0.5, 0.8, small, medium, and large. So clearly 1.82 gives us a large effect. And we can kind of think about that as that the difference in this these two means is something that can be detected simply by eyeballing it. This would be something that would not be detected just by eyeballing the difference. All right, so that difference, the effect size for that difference is represented by a large effect. All right, gang. Again, I've got to fight it. There's so many rabbit holes I want to go down into right now, but not going to do that. Take care.